Dear friends and colleagues, I wish you all very welcome to this webinar on modeling on phototrophic systems for resource recovery from wastewater. This webinar is an effort from the IWA specialist group on modeling and integrated assessment. And we use this webinar series to highlight various aspects of topics related to modeling. And this is the 14th webinar that we organize. My name is Dr. Ulf Jeppsson. I'm from Lund University in Sweden, and I'm the chair of this MIA specialist group, as we call it, Modeling and Integrated Assessment Specialist Group. Before we start the actual webinar on the phototrophic systems, I would just take this opportunity to say a few words about the work of the MIA specialist group. We are one of the most active specialist groups within the International Water Association, and we are the specialist group that is really focusing on modeling of all aspects of water and wastewater and everything related to water and wastewater as well. The specialist group is open to everybody who is a member of IWA, and we currently have some 1,900 members in our group. One of the most important ways that we work is through task groups. At this point, and the task group is normally just a small size group of specialists who is focusing on a specific topic. They do that for a number of years, and then normally they produce an IWA scientific and technical report towards the end. Currently, we have two active task groups: the membrane bioreactor modeling and control task group, and the good modeling practice in water resource recovery systems. But as you see here to the left, we also have had a number of task groups that have recently or some time ago finished their work. And I want to mention the STRs that you see here to the right: the uncertainty in wastewater treatment design and operation, and the STR on greenhouse gas modeling. They were both finished fairly recently, and they are both available as open access, so everybody can download the entire report from IVA Publishing. We also work through working groups, and working groups is often a larger group of persons that are promoting and investigating often a more general topic, and do that and write white papers and lobby for their area, and may do special workshops at conferences and so on. And finally, our third way of reaching out to our members is through conferences, and we have two main recurrent international conferences: the WRR Mod Conference and the Watermatics Conference. I want at this time especially promote this scientific and technical report, the STR on physical-chemical modeling. That was published just about a month ago, and it is also available open access, so everybody can download the entire report from IVA Publishing. Don't miss on this opportunity. It's a great report. Speaking of conferences, we have some upcoming conferences under the MIA umbrella. We have our next Water Resource Recovery Modeling Seminar, also known as WRR Mod. That will be held in Stellenbosch in South Africa in the mid of January, 18th to 21st of January next year. and it's organized by Dr. David Ikumi and his colleagues at the University of Cape Town. Then towards the end of the summer 2023, late September, we have our Watermatics conference, symposium on modeling and integrated assessment, and that will take place in Quebec City in Canada, and will be organized by Peter van Rollegem and Elena Torfs. And then we also have almost decided upon that the WRR Mod conference in 2024 will be in Stove, Vermont in the US. There are still some details about that one to conclude, but everything is pointing in this direction right now. If no one hears what MIA is about and what MIA achieves and what it's doing, we hardly exist. And therefore, we have a number of channels for you and others who want to learn more about our activities and follow news and updates and so on. We have our official website on IWA Connect for IWA members. But we also have an open website. So if you're not an IWA member, you can find in principle the same information on this open website. And then we have our LinkedIn group, and we have a Twitter group. And we also have a YouTube channel where, for example, this webinar will end up, the recorded version of it, and a newsletter and a digital archive and so on, all to make it easier for our members to keep track of what is happening within the specialist group. So if you're not already a member, we certainly hope to see you very soon as members of the MIA specialist group of IWA. With that, I want to leave the floor to Dr. Elena Ficara from Politecnico di Milano in Italy to introduce the topic of today, and I wish you all a very fruitful webinar.
Hi, thank you, Ulf. And thank you to the Modeling Integrated Assessment Specialist Group for inviting me to chair this exciting seminar. Hi, everyone, and a special thanks to our speakers of today for joining the seminar and contributing to this seminar. And welcome to you all from me as well. So as already introduced by Ulf, my name is Elena Ficara. I am an associate professor at Politecnico di Milano in Italy. Very just few words about myself. I graduated as an environmental engineering at Politecnico di Milano, and I got a PhD in sanitary engineering dealing with the titrometric and respirometric techniques for the monitoring of biological processes. I'm a member of the IWA, of the European Algal Biomass Association, and I'm in the steering committee of the Italian Microalgae Association as well. My main research interests are basically related with biological processes for bioremediation and resource recovery. And I had been working with different microorganisms, but since few years I've been focusing on the applications of microalgae in the bioremediation of urban and agro-industrial wastewaters, with special attention to digestate. So I'm especially pleased to shortly introduce and frame this seminar topic before leaving the floor to our speakers. As you may well know, phototrophs are newcomers in the field of wastewater treatments, and they have been attracting increasing interest from scientists and practitioners. And they have a number of interesting abilities, especially they possess the ability to use solar energy for fueling their metabolism. And they produce new organics and even high value molecules. Within phototrophs, microalgae, they are able to capture CO2 while producing oxygen by photosynthesis, while purple bacteria, they perform an oxygenic photosynthesis, showing very flexible metabolic pathways that are regulated by the environmental conditions they're exposed to. Like other conventional microorganisms, they can contribute to wastewater bioremediation by assimilating nutrients, by providing micropollutant removal capacities, by favoring disinfection. So that are all properties that justify the interest for these organisms. But of course, when dealing with new microbes, new challenges come up for microbiologists, but also for process engineers, and more relevantly here for the modeling community. Just to mention a few, we have to understand and describe new metabolic pathways, especially for the dependency from light availability and intensity. We need to integrate new physicochemical phenomena, especially light penetration, which is quite essential in phototrophic systems. We have to understand and describe the interaction of these microbes with others that coexist, like conventional heterotrophs and chemotrophs. And finally, we had to devote some attention to the specificity of the reactors and fluidodynamics of these systems that are designed in order to offer an efficient light capturing ability. So all these topics will be discussed by our speakers of today. So let's have a brief overview over the agenda of the seminar. So our first speaker is Gabriel Acien Fernández. He will discuss microalgae-based nutrients recycling processes. Then we will move to Francesca Casagli. She will discuss the algae-bacteria systems and the modeling of them, of these complex systems. Then we have Borja Valverde Pérez that will discuss the modeling of light distribution in photobioreactors, while our last speakers, Gabriel Capson Tojo, will discuss Purple Phototrophic Bacteria and how to model outdoor system based on this Purple bacteria. Finally, we will have a question and answer section. Just a few technical notes on the managing of the seminar. As you have to be aware that this section is recorded, but your microphones and cameras have been disabled, as well as the chat function. So if you have any, put your questions and comments using the question and answer tool. There's an icon for that you can find in the low right section of the toolbar in Zoom. Use that. We will do our best to answer your comment and questions during the section, while those that may require more discussion will be resumed at the end of the speaker section, at the end of the sections, and we will then discuss more in details those questions. So let's move to our first speaker. Let me introduce Gabriel Acien Fernández. Gabriel is a professor of chemical engineering at the University of Almeria. He's a secretary at the European Algae Biomass Association, and he's a member of the International Society for Applied Phycology and Latin American Society of Algae and Environmental Biotechnology. He's a well-recognized scientist in the field of microalgae, and his major contribution to the microalgae field are related to the improvement of photobioreactors design, to the scale up of production systems, and to the economic analysis of production processes, as well as to microalgae biomass valorization to improve the economic feasibility of microalgae-based processes. So thank you, Gabriel, to be here, and the floor is yours.
Thank you very much, Elena. Thanks for the introduction. I will try to share my screen. I think that now, can you see
yes
properly?
Yes.
Okay. Thank you very much. I want to more or less to summarize in this presentation the activities that we are performing. We already performed at the University of Almeria related with the recovery of nutrients from wastewater using microalgae. This is mainly part of the
Gabriel,
project of the Savannah
Gabriel.
project that we already conclude in the last years.
Gabriel,
This
sorry.
project was developed.
Gabriel,
Sorry, I have some
just,
problems with my microphone.
you're not in full presentation mode, Gabriel.
Ah, okay, sorry. I think this is a question of the. Now?
Yes,
Right?
good. Continue, please.
Okay, thank you very much. Okay, I repeat that this type of research has been mainly related with the Savannah project that we conclude in the last years. In this project, we aim to develop large-scale production system, integrating the recovery of nutrients from different effluents. Then I want to remark the participation of Biorizon Biotech, Aqualia, is the one of the larger wastewater treatment companies in Europe and especially in Spain. Okay. Then, as part of this research, we perform different activities focused in the production of microalgae, more sustainable production of microalgae, using different effluents as sewage or centrate from urban wastewater treatment plants, but also other effluents for agro-industry, including manure and digestates, also from farming activities. I want to remark that the use of all these effluents to produce microalgae is possible. The only challenge is to be able to adjust the dosage of these effluents according with the nutrients and phosphorus content. The COD is not so relevant. And the other major factor is the turbidity, because it largely affects the light penetration in the cultures and then the final performance of microalgae cells. In addition to some, basic research about the models, the interaction between bacteria and microalgae that other speakers will explain in more details, we mainly focus in the the validation of these technologies in large scale system. Then for more than 2 years, we has been operating 2 parallel reactors, one treating wastewater from the University of Almeria and the other one operated with fresh water and fertilizers. And we already confirmed the reliability of these technologies in pilot scale system all the year around. And of course, we need to adjust the operational conditions as a function of environmental parameters, mainly temperature and solar radiation availability. In average, the optimal dilution rate for the system corresponds to 0.2 days -1, then 5 days of hydraulic retention time. I want to remark that operating this reactor in real conditions, we are able to accomplish the regulations in terms of removal of pollutants and nitrogen, phosphorus, the low concentration of whatever microorganisms, contaminant, bacteria, and whatever, and especially the large benefit of this system for the recovery of nutrients, especially nitrogen and phosphorus, up to 30 kilograms per hectare and per day, nitrogen, and 2 kilograms per hectare per day of phosphorus in the real facility. This knowledge has been shared with the company, with Aqualia, and after 2 years of projects, they were able to install real demonstration facilities. The ones already being in operation in Egin, 1 hectare in a single reactors, and 2 hectares of raceway reactors treating wastewater in the town of Merida. Previous experience were also related with the use of microalgae for wastewater treatment, were installed in Chiclana and also here in Almeria. But I want to remark that these facilities are currently only devoted for wastewater treatment. I mean, there is not other options to treat the wastewater in this village, in these towns, especially in Egin. Data from Aqualia, more or less demonstrating the reliability of these technologies, confirm the quality of the system to be able to remove the organic matter, the COD, to reduce the COD from 500 at the entrance to 25 at the outlet, and the efficient removal of nitrogen and phosphorus from the inlet stream to the outlet streams. Then also to confirm the large production of biomass in this type of technologies. In summary, probably you know this figure because it's more or less an example of the capacity of the technology. In only 1 hectare, it is possible to treat the wastewater produced from a 5,000 equivalent person municipality. more or less the flow is in the range of 1,000 cubic meters per day. Then, in addition to reuse, to recover water for other uses as agriculture or golf fields or whatever, the technology is able to reduce a lot the energy consumption of conventional technologies, to produce a large amount of biomass suitable to be used for biogas production, for biomethane, useful for cars, and also to produce biomass as fertilizers. In Almeria, because we are more closely related with agriculture, we already explored the possibility to use the microalgae biomass being produced from wastewater treatment, and we confirmed that this biomass is really useful for biostimulants application in agriculture, both in greenhouses and also in our ornamental crops, etc. To summarize the major effects that we detect in the samples is that providing in the range of 10 kilograms of microalgae biomass per hectare, we observe a large development of roots of the plants. I mean, this is called the auxin-like effect. And then this large development of roots contribute to the higher production of fruits and the better quality of the products being obtained. This is a separate trial in which we don't use wastewater. We use manure as nutrient source for the production of microalgae. The biomass being produced, in this case was marine strengths, was also incorporated in aqua feed. Then the feed was really well appreciated by the fish. We don't observe any problems concerning palatability or acceptability of this aqua feed for the fish. And also we observe a large increase in the quality of the fillets and the performance of the fish being produced. Then that's all from my side. I want to show you more or less the capacity of this technology to really contribute to the bioeconomy in this sector. Thank you very much.
Thank you, Gabriel. Thank you, that was very interesting. We will, as said before, we will keep question time at the end of the section. So I hope you can wait for a few more minutes and then we will take questions for you. And now we will move to the second speaker of today. So I'm pleased to introduce Francesca Casagli. Francesca graduated in environmental engineering at the University of Florence. In 2017, she started a PhD in environmental and infrastructure engineering at Politecnico di Milano, focusing on mathematical modeling of algae-bacteria systems for wastewater bioremediation. During this PhD, she spent 1 year at INRAE in Narbonne, France, to calibrate and validate her model on long-term data sets. After defending her PhD thesis in March 2021, she got a postdoc position at INRIA Biocore team, where she worked on the optimization of algae-bacteria systems. And since the September 2022, she is permanent researcher at INRIA Biocore team. And now she's focusing her research on experimental design and modeling of N2O emission. And recently she has been awarded with the prize for Women in Science from L'Oréal, UNESCO. So thank you, Francesca, for being here, and the floor is yours.
Thank you, Elena, for the presentation. I will try to share my screen. Okay, can you see the screen? Okay, I guess yes. So thank you, Elena, for the presentation, and thank you to the organizer of this seminar for having invited me to speak. I'm going to speak about our algae-bacteria system for nitrogen recovery and biomass production with all the promises and challenges through a modeling approach. So in algae-bacteria bioremediation system, we are dealing with outdoor reactors, the raceway ponds, where the input are the local climatology, the nutrients, and the wastewater, source of inorganic carbon. And then as output, we have treated water the algal biomass, and also emissions. And the main advantages of this kind of system is that we can recycle energy, nitrogen, and phosphorus contained in the wastewater. We can also produce valuable products, fiberizing a circular economy through the algal biomass, and we have reduced costs for aviation system. But we have also some bottlenecks. For example, the fact that these systems are outdoors, so they are completely subject to uncontrolled environmental conditions, mainly light and temperature, according to the local climatology. Then there is the solid liquid separation when uncoupling the hydraulic retention time and solid retention time, and to see if it's really worth it. And also emissions of different gases and inorganic carbon limitation conditions. And to understand how to deal with these bottlenecks, we are using mathematical models to try to solve them. And the main challenges with mathematical models is that we want to consider together the biological, chemical, and physical aspects, and also validating the model, the framework on long-term data set to quantify the emissions, but also more in general the fluxes, and accounting for a separation system. So in other words, to try to understand what we cannot see, so the invisible. So now I'm going to quickly introduce you the modeling framework structure that we developed. There is a biological model, heat transfer model, and a chemical model interconnected among them, and also a module for the meteorological data and the input-output fluxes. And concerning the biological model, we are modeling the interaction among the phototrophic algae, heterotrophic bacteria, and nitrophile bacteria. And the structure of the biological model is inspired to the activities large and anaerobic digestion model through the stoichiometric metrics. Then we have the state variable vector with biomasses and particulate and soluble compounds, and also the vector of reaction rates of the biological processes. For example, here, the growth of algae, and also the gaseous exchange with atmosphere. And more recently, we added a module for the prediction of nitrous oxide fluxes that was calibrated with dedicated experiments. Then we have the heat transfer model that is very useful to predict the temperature inside the reactor. It was adapted to two raceway configuration when it's lying on the ground or when it's rise up from the ground. That is a typical pilot scale application. And then we have also the chemical model that is based on mass balance of the dissociated species, the dissociation of soluble species, and of course the charge balance. And it's very important because thanks to it, we can also compute and predict the total alkalinity of the system. And I will show you later on why this variable is that important for this kind of system. So this framework was tested on 3 different experimental campaigns, one in Arbonne, one in Milan, and one in Rennes. And here are the pilot scale application and the number of days on which the model was tested, and the influent that was using the 3 different applications. And very quickly, I'm going to show you the model prediction capability. In this case, just in terms of total ammoniacal nitrogen removal rate according to the different season and also to the different experimentation. And here, I'm showing you the validation of the model when applying a membrane separation system for uncoupling HFT and SRT. Here, in terms of biomass productivity, you can see the experiments and the simulation results according to different seasons. And in terms of nitrogen removal rate, here the experiments and here the simulation results, even in this case, according to different seasons. And as you can see, the model reproduces quite well the experimental data, the measurements of the 3 different experimentation. Now I'm going to quickly speak to you about a very important aspect that is the inorganic carbon limitation and the nitrous oxide production and emissions in this kind of system by ammonium oxidizing bacteria. Because through the model, what we notice is that when you are growing algae and bacteria on influent that are very rich in ammonium, as for example digestate, even if you have a pH regulation through CO2 bubbling, you can have inorganic carbon limiting condition. And this is a real problem for several reasons, because you have lower nutrient removal efficiency and also higher emissions in terms of CO2, ammonia, but also nitrous oxide. In fact, we found in several work in literature that when inorganic carbon is very low in concentration in your system, this can trigger the nitrous oxide production by ammonium oxidizing bacteria. And running additional simulation, we found out that the problem was a lack in alkalinity in your system. So the buffering capacity of the system was completely consumed by the nitrifying activity. And so in this case, the solution was really not only to control the pH, but also an alkalinity regulation of your reactor, of your system. Indeed, to check that this is what was really happening in the real reactor, not just in the model, we ran dedicated experiments in REN at the Gray laboratory, where we had 3 different raceways of 400 liters each. And basically what we did is to feed the raceway with diluted and centrifuge piggery digestate. And then in the first reactor, we also added a source of ammonium to unbalance even more the ratio between ammonium and alkalinity. In the second reactor, we had just diluted the digestate. And in the third reactor, we added also a source of alkalinity. And this is the experimental setup in REN. Then for measuring the dissolved nitrous oxide in the reactor, we applied the salting out method. Basically, we were putting samples of our reactor in oversaturated solution of salt to enhance the nitrous oxide stripping. And then we were analyzing the gas phase in the bottle with gas chromatography and electrocapture detector for determining the concentration that previously was in the liquid of nitrous oxide. And now I'm going to show you very quickly the results, both in terms of measurements and simulations, starting from the pH dynamics. What we can see is that in the reactor where there was the lowest level of alkalinity, the pH dropped down after a few days. And even in the reactor with just diluted digestate, but this is not happening where we added a source of alkalinity. And concerning the ammoniacal nitrogen, what is interesting to notice is that in the first reactor with low level of alkalinity, the ammoniacal nitrogen is not totally consumed, while it's totally consumed in the reactor when we added a source of alkalinity. And why is happening? This is happening because in the first reactor, the inorganic carbon is dropping down to 0, first in the one with the lowest content of alkalinity, then in the second reactor, but this is not happening in the reactor where we added a source of alkalinity. And here you can see the trend of the nitrous oxide production rate, the simulation and the experimental data. And what we can see, computing an average and standard deviation of the days of experimentation, is that the biggest flux of nitrous oxide is in the reactor with the lowest content of alkalinity, while the lowest flux of nitrous oxide is in the reactor where we added a source of alkalinity. And it is also very interesting to notice that if we compute the fixed CO2 in grams CO2 square meter per day by algae, so the green column, and we compare it with the emitted nitrous oxide in CO2 equivalent, we can see that in the worst case, so the reactor with lowest alkalinity, the nitrous oxide flux is higher than the fixed CO2 by algae. That is not at all what is happening in the reactor where we added a source of alkalinity. Then, remaining in the topic of manipulating the alkalinity in our reactors, but also uncoupling the hydraulic retention time and solid retention time and varying also the liquid depth, we are going to see what is happening through a modeling study. So here I'm showing you the simulation results in terms of algal productivity, nitrogen recycling efficiency, recycling in the algal biomass, and the nitrous oxide risk factor for 2 different liquid depths, 22 centimeter and 6 centimeter. And with an alkalinity content, there was the nominal one in the digestate we were using. And what we can notice, we can see, first of all, that the pair of HRT-SRT that are maximizing the algal productivity for both the liquid depth are not the same pair that are maximizing the nitrogen recycling efficiency. And also, that the values of HRT-SRT that are maximizing the nitrogen efficiency for both the liquid depth are in an area where there is the highest nitrous oxide risk factor computed depending on the available inorganic carbon dissolved in the medium. So we run additional simulation, increasing the sourcial alkalinity up to 22 mole per cubic meter. Now I'm showing you the results just for the liquid depth of 6 centimeters. And what we can see is that the nitrous oxide risk factor dropped down to 0. And also that we gain something for the nitrogen recycling efficiency. And concentrating a bit on the algal productivity, maybe we can concentrate on this graph that is a bit more clear. In blue, we have the scenario where the HRT is here, the red dot line, is adapted according to the SRT for maximizing the algal productivity. While in green, we have the scenario with no solid liquid separation, so HRT equal to SRT. And indeed, we can see that we have a gain in the productivity of algae when uncoupling the hydraulic retention time and solid retention. So in conclusion, I presented you a general framework for simulating the outdoor ecosystem, the biological, the chemical, and the transfer module. I show you that when we are growing algae on wastewater that are rich in ammoniacal nitrogen, if these systems are very low in alkalinity content, the emitted nitrous oxide can be larger than the fixed CO2 by algae, and increasing alkalinity is indeed the solution to enhance the process efficiency and avoid, or at least to reduce the nitrous oxide emissions. Then we saw that decoupling the dry retention time and solid retention time turns out to be very efficient, but just when combined with liquid depth adaptation and also alkalinity addition for avoiding nitrous oxide emissions. And we also saw that we cannot maximize simultaneously the efficiency, nitrogen recovery in the algal biomass and the algal productivity. So if these two objectives are the goal of your system, we have to find a trade-off between. I want to stress the fact that, again, modeling is really a very important tool to guide us in the understanding of this very complex nonlinear dynamics of this kind of ecosystem. And in the future, we want to focus on optimizing the process operation also on a daily basis, so varying the operational parameters during the day to optimize the process. And thank you very much for your attention.
Thank you very much, Francesca. I think you were quite convincing on the usefulness of developing such complex models for the understanding of these complex systems. So thank you very much. And please stay with us till the question and answer section. So let me just mention that the slides that that the speakers are using right now will be made available for all registered participants to the webinar as a PDF in a few days. And I'd also like to remind you that you can use the question and answer tool to reach out to our speakers and to discuss with them. So don't be shy, please use the tool. And now I think it's time to move to our third speaker. So next presentation is going to be from Borja Valverde Pérez. Borja graduated as chemical engineer at the University of Santiago de Compostela in Spain and specialized in bioprocess design and control. He pursued a PhD at the Department of Environmental Engineering at the Technical University of Denmark, focusing on resource recovery from municipal wastewater, combining activated sludge processes for removal, for nutrient removal and microalgae cultivation. Currently, he is appointed as associate professor at DTU Sustain, working on environmental biotechnology and water treatment, combining both empirical studies at laboratory and full scale with modeling tools for process design, optimization, control, and sustainability assessment. So thank you, Borja, for being with us, and the floor is yours.
Thank you, Elena, for this nice presentation. So today I came here to talk a little bit about light modeling. You have already heard a lot about what are the benefits of using algae to capture nutrients and carbon in wastewater treatment plants. So, and you have also heard a bit that light is important for these microbes. So I want to explain you today, how do we account for these light effects, right? The agenda is pretty straightforward. I will first introduce a bit on what is the impact of light on algal growth. Then I will explain a bit of what are the main factors that affect the light attenuation in the photobioreactors. And finally, I will show you a couple of modeling approaches to tackle this light issue and what is the outcome of each of these. The work that I'm going to present has been done with a mixed culture. So it's the one you have in the figure here. You can see we have Stenodesmus, we have chlorella, and we also have some diatoms in our experiments. The first thing we tried to do is to assess what is the impact of light on this mixed culture that we had in our lab. And to do this, we operate these really tiny, small reactors that you see here. We started with a very small scale. We are talking about 2 milliliters. And we cover them with this coverage here. You can see that there is kind of a shading effect. So you can actually control how much light intensity you give to each of these rows. And with this kind of experiment, we can actually get what is the dependence of growth rates on light availability for the algae. And these reactors are so narrow that actually you do not get light attenuation through them. What you observe in the figure on the left is that actually the growth rate of the algae increases with increasing light intensity until you reach a sort of maximum beyond which your algae starts suffering from photoinhibition. This is a phenomenon that affects many of the microalgae that we use for wastewater treatment. And it can be very well modeled by this kind of expressions. This is just one example, the still equation, where we can modulate the growth rate of the algae if we know the maximum growth rate and what is the optimum light intensity that they have. So this is how they depend on the light, but how is the light distributed in the bioreactors or in the photobioreactors? Well, we know that the algae, they absorb the light because they have to use it for carrying out the photosynthesis. We also have other phenomena like can be this light scattering. So basically when the light hits your algae or hits the walls of the reactor, they change direction and or the light changes direction. And this is what we call a scattering. The algae can induce self-shading to each other. So they can shadow each other. And then finally, all these effects are also more or less enhanced depending on the pigment content that your algal biomass has. Mostly we focus on chlorophyll and carotenoids. How we analyze this effect is with this kind of column reactors that you see in the figure. What you see inside the column is a light sensor that we could move up and down, so we could get the light intensity as function of the depth in the photobioreactor. So we tested this in 3 different configurations because we wanted to assess if the geometry of the photobioreactor plays a role on how the light is being distributed, and if we can account this with modeling. And then we also tested different conditions. So we tried different biomass concentrations. We tried to starve this biomass to induce changes in the pigmentation. And we also worked with synthetic media and also wastewater as cultivation media. So we can actually compare the absorption or attenuation depending on the matrix for algal growth. What we found out is that all cases, the nutrient availability, the biomass concentration, and the cultivation media we were using, they were playing major roles into how light was being distributed in the photobioreactors. We found that the scattering was actually quite important when we have algae in nutrient-limited conditions. This means that your algae in these conditions usually decrease the content of chlorophyll, which somehow enhance the scattering effect. We have also observed this in the narrowest reactor. So when we have the shortest diameter in our reactor, there is more scattering effect we suspect from the walls, which also highlights an effect on how we model the light distribution. So with this experiment that I described, we get this kind of curves here. We have different curves or data series depending on the concentrations of algae that we have. And what you can see is that there is a very steep absorbance or attenuation of the light in the first centimeters. That's why we tend to design photobioreactors that they are not too, or they are relatively shallow. And you can also see that the higher the concentration, as expected, your light is going to be more attenuated through the photobioreactor. So this kind of data series, we can feed them to the Lambert-Beer law, which is commonly used to describe attenuation of light in any matrix. And in this case, as you can already see, we expect that this law is going to behave differently depending on which algae concentration we have. And this is actually the case when we estimate the absorption coefficients. We see that the attenuation coefficient for the different biomasses have different values. In the bottom case here, we worked with treated wastewater to grow our algae, and we see that the matrix effect kind of buffers the effect of the concentration of biomass. However, when we use synthetic media and we starve our algae, the effect of biomass concentration is quite significant on the attenuation coefficient and becomes really, really important to have an accurate estimation depending on the biomass concentration. So the main difference between this orange and the green curve here is the pigment content. Because in the orange case, we had them the algae starved, while in the green one, we had them with a lot of nutrients. So how did we account for pigments? We ran a batch experiment in one of these column reactors. We had like an 8-liter reactors where we grew the algae and we monitor nutrient uptake. But on top of that, we also look into pigment content. So we can actually see what is the content on the chlorophylls and the carotenoids. On the right side, the carotenoids, you can already see that the concentration is not so high. So actually our focus was mostly in chlorophyll. You can see chlorophyll A is the main pigment that the algae or our mixed culture was storing. So for each of the data points that you have here, we have made a test where we look at or estimated the absorption or attenuation coefficient of the media in the photobioreactor. And then we could fit actually the attenuation coefficient as function of the chlorophyll content. So this kind of approach becomes very useful if you actually have a model that is able to predict pigments. So once we know how this, or we have now a good knowledge about how the light distributes in the photobioreactor, the next question is, okay, how do we model this? And if you go through literature, there are 3 main approaches to model light intensity. So researchers, especially in the past, they just assume that there is an average light intensity through the whole period, regardless of the biomass concentration that you have. And they just try to fit all the biokinetic parameters to predict the data counting just with this average light intensity. Some other groups, they have accepted that you have some variability in your attenuation coefficient, which depends on the biomass density. So they recalculate the average light intensity every time that they simulate a new data or a new biomass concentration in the photobioreactor. So they have some sort of dynamic average light intensity. And then the last model is a little bit more complex. So it's not so widespread, I would say. But what this model aims to do is takes your photobioreactor, as in this figure, and discretize it in several layers. And then it estimates what is the average light intensity in each of these layers as function of the biomass concentration that you have in the reactor and how the light is being attenuated. So the growth rates that you experience in each of the layers, it's going to be different. We decided to compare the 3 of them. So you have here the average light intensity, the variable average light intensity, and the layer model. And we tried to see what was the effect of the predictions of all the state variables that we were modeling with our biokinetic model. So here you see quite complicated table, but let's focus on algal biomass. When you look into the error on the model predictions, we can see that actually you reduce it when you increase model complexity. So when we have a layer model, the error is significantly lower when we predict algal biomass. And if you look into the Akayaki's information criterion, it's actually the same, or it gives the same suggestion that the layer model is much better to predict algal biomass concentrations. So this is very important to take into account if your aim in modeling is actually predict biomass quantity. If we look into the last parameter, this is a relation between the uncertainty of the model, so how wide is this blue area, and the amount of data that it covers. So how many of this experimental data can be covered within the uncertainty that your model has. And the lower it is, the better it is. So what we can see is that the layer model reduces a lot the uncertainty of our parameter estimates, or our model output, sorry. But at the same time, it has a pretty good coverage of the empirical data. So it seems to be the best option actually for having an accurate modeling of our photobioreactors. When it comes to the parameter estimates, there is some variability when we have different models for light intensity. You can see it's most significant in the maximum growth rate and in the maximum uptake of nitrate. And this is because of this effect that we have when we average the light, assuming that all the algae will grow at the same velocity, even though in the bottom of the photobioreactor, the growth rates will be lower. And with this, I go to my conclusions of the presentation for today. So the first thing that we show you today is that the growth rate usually it grows with light intensity until you reach a maximum beyond your algae suffer photoinhibition. This maximum varies a lot from species to species. Then we also saw that the light attenuation has a strong dependence on the pigmentation and the biomass concentration, and this is something we should take into account when estimating the light exposure on our algae. And then finally, what we saw is that when you discretize your model or your photobioreactor to predict the distribution of light intensity, you get much more accurate predictions of the microalgal biomass concentration, especially. This research has been published in these two papers that you're welcome to go and check if you want to learn more details. Else, you can ask me today. And otherwise, thank you for listening to me this afternoon or morning, depending where you are.
Thank you, Borja. Very nice presentation. It is definitely relevant to the topic of phototrophic systems to understand the role and the role of the light and how it affects the activity of phototrophs. And I think you provided a very nice framework on how to deal with it. So thank you again. Time to move to our fourth presentation. That it will be provided by Gabriel Capson Tojo. Gabriel studied chemical engineering at the University of Santiago de Compostela in Spain. After that, he enrolled in a Master of Science of Environmental Technology within the Erasmus Mundus program, coordinated by Ghent University. He made his PhD at the Laboratory of Environmental Engineering, Environmental Biotechnology, of INRAE in Narbonne, France. After that, he worked as a research engineer for Suez, Paris. In 2019, he started working on Purple Phototrophic Bacteria as a postdoctoral research fellow from the Cretus Institute of the University of Santiago de Compostela, Spain, in collaboration with the University of Queensland in Australia. And since early 2022, he is a researcher at INRAE, LBA. And his research interest moves around the concepts of circular economy and resource recovery from waste streams. His main areas of expertise are anaerobic digestion of solid waste, resource recovery from wastewater using Purple Phototrophic Bacteria, and biological gas conversion. Thanks to Gabriel for being with us. And the floor is yours.
Thank you. Thank you, Elena, for the introduction. So I'll move ahead and go for the presentation. Hope you can see my screen. So I'm going to change a bit.
Gabriel,
Yep.
can you activate your camera as well?
It says that the host has stopped the video and I cannot do it. So probably you have to do it.
Yep, continue with your presentation. I will try to solve it. Yep.
Yeah, thank you. So We'll go ahead and start the last presentation, which I'm going to move away from algae, and I'm going to move to purple bacteria, which are fundamentally very different organisms. But of course, there are phototrophs also, so there are a lot of similarities in terms of application and the type of reactors and what can we use them for. And there you go. All right, so I'm going to start with a brief introduction about purple bacteria, or PPB. And as I guess most of the audience are not familiar with them. And the first thing to say is that they are anoxygenic phototrophs, which is a main difference with algae. And what this means is that they don't use water as electron donor, but other different compounds. And that leads to a very big difference with algae, is that you don't produce oxygen during the photosynthetic processes. Therefore, the name anoxygenic. And they can be classified into different groups, usually depending on the electron donor they use. If they use H2S, they are called purple sulfur bacteria, pretty obvious. And there's also purple non-sulfur bacteria, which, despite of the name, they can also use H2S, but they can use a different wide range of different electron donors, reduced metals, hydrogen, and even organic matter. And just to give you an idea of which are the common genera that we find in our reactors, Rhodobacter, Rhodomonas, and Elastoparis are among the most the predominant genera that we have. So why are we interested in PPB for resource recovery? So PPB are among the most versatile microorganisms on Earth regarding their metabolism. And in terms of resource recovery, this phototrophic growth here is what interests us the most. Basically, in this process, they are able to use organic matter as carbon and electron source and light as energy source. And why we are interested in this is because this allows biomass yields close to 1 gram CO2 per gram CO2 consumed, which is always interested if you want to recover organic matter and energy. They provide a simultaneous CO2 and nitrogen and phosphorus removal, just pretty much like algae. It's an assimilative process, so it's biomass growth, which leads to removal. They, opposed to algae, also they use near-infrared light mostly for growth, and that's a feature that is almost exclusive for them, which means that you can enrich them from virtually in waste stream. And they have around 60% of protein content, which means that you can use them eventually for single-cell protein source. So, as I was saying before, they have a very versatile metabolism, and depending on the environmental conditions, they will grow via one different mode or another one. And here I just want to show, if there is oxygen or organic matter, they will grow via respiration. If there is organic matter and anaerobic conditions in the absence of light, they will ferment. And obviously they will grow autotrophic if there is light. And the main challenge here in terms of model is, one, you got a lot of metabolisms to model within a single microorganism. As you can see here, this is the scheme of the first model that was proposed for PPB, for resource recovery. And what you can see here is that you got a bit of everything. You got fermentation in aerobic conditions. You got obviously autotrophic growth. You got light uptake. You got ammonia and CO2 fixation and anabolism, etc., etc. And to make things a bit worse, usually we don't have pure cultures, obviously here. So we got mixed cultures and usually grown outdoors, because basically for application purpose, just like algae, you need, well, artificial light is economically not feasible. So you need to include competition with under each of these metabolic growths with the corresponding organisms that will compete with PPB, and you also need to include variable environmental conditions. And that's what we did, basically. We include hydrolysis. Basically, we had a very nasty wastewater to model, and in the previous model was coupled. We added the aerobic metabolism of PPB. We included microbial interactions with algae, aerob fermenters, sulfur-reducing bacteria, and others. We included inhibition factors, mostly related to the presence of oxygen and pH. And as Borja was saying before, light availability and attenuation is crucial, so we include that there. And we also include the variable temperature, because obviously in a system outdoors, that changes dramatically. So we started doing experiments because we barely had any data at the moment. And the first thing that we did was in a very similar way to what Borja described before, we determined the uptake rates, different light intensities, which is what you got here. And we use a model to do that too. Very similar to what Borja described. When the main difference, we didn't see a scattering as a relevant term, but so the Lambert-Beer function worked nicely. And we also had, as you can see here, very different attenuation profiles at different biomass concentrations, which are these values here. So we also needed to modify the attenuation coefficients depending on the biomass concentrations. We also determined the uptake rates at different temperatures, which is what you see here. It was a CTMI curve, the model that we applied. And just to give you an example of one of the inhibition tests that we did, the enrichment here, which has color, was performed under anaerobic conditions. And here it was an experiment carried out under microaerobic conditions. So totally loss of color and inhibition of phototrophy. And so we put all this together, together with a biological model and a chemical model, pretty much what Francesca also presented. And we ended up with something pretty complex, basically because of all the organisms that we described before and all the processes. So 30 processes, 21 states, plus equilibria. And I'm not going to go through the whole thing, doesn't make sense. But most important things to consider here, we took into account different metabolisms of PPB. We were forced to separate acetate from the other lumped BFAs because their uptake kinetics were different. But you can see here that we included phototrophic growth of PPB, fermentation by PPB, and aerobic respiration by PPB also. And obviously, we needed to include all the different competitors that we had for each of those processes. So we added aerobic heterotrophs, we added fermenters, which is what you have here, acidogenic and acetogenic bacteria. We needed to include also predators, so grazers, because it was the only way that we could explain the biomass yields that we had under aerobic conditions. And as I was saying at the beginning, they can use PPB can use H2S for growth. So we needed to include also sulfur-reducing bacteria. And we included here pretty much heterotrophic and autotrophic SRBs to cover the whole spectrum. And we also needed to include microalgae. As I was saying before, we're working outdoors. And even if we filtered the light that was getting into the reactor to minimize the presence of visible wavelengths, we still got some passing through. So we had microalgae, which obviously affected the nutrient removal rates mostly. And some inhibition factors, as I was saying before, oxygen, light, temperature, and pH, and obviously nutrient requirements and ammonium nitrogen. So in terms of experimental data, we ran this reactor here, which was a 10-meter reactor with approximately 1 cubic meter in volume at the University of Queensland. And we run it under different HRTs, OLRs, and very variable temperature and maximum irradiance. And we use this for calibration and validation of our model. So that's the calibration that we did for phototrophic conditions. So anaerobic, illuminated, and presence of organic matter. And what you see here is that obviously after calibration, the concentrations of BFAs were predicted relatively nicely, and the same thing for ammonia and phosphorus. And when we moved to validation, the first thing that we did was using data from batch tests, mostly because we wanted to test both anaerobic and aerobic conditions. And this is what you see here in the left. These are the anaerobic results, and as you can see, the model was able to predict pretty nicely the SCOD consumption, as well as the kinetics of nitrogen and phosphorus consumption. We had a bit of an offset here, which we think is due to increased death rate at the end of the batch tests, but we still need to check it out. And but what was most important for us here is that the model was able to change automatically between anaerobic and aerobic conditions, even if the starting conditions were the same. And the model was able to represent the much faster kinetics under aerobic conditions, which were basically due to a total out-competition of PPB and the growth of heterotrophic biomass, which is what we saw experimentally too. And again, the nitrogen and phosphorus were relatively accurately predicted. And this difference that we see here is, well, they are mostly because we assume the biomass composition as constant in all the different bacterial plates that we consider, and that's probably not true. So something to also have a look at in the future. When we validated the model using data from the flat plates that I showed you there, the SCOD, TCOD, and nitrogen and phosphorus graphs we were happy with them. And of course, I leave the words for the end. And the two that you see here are acetic acid and BFA separately. And what the model predicted here was basically what happened during nighttime, that we didn't have removal, but we had basically organic matter accumulation that was fermented during nighttime. So, but there was no light to remove it. So you have these accumulation peaks during nights that are consumed during daytime, and the same thing happening for BFAs. And the problem here is that we didn't have enough data of daily cycles to validate this. So still, we were happy enough that we were able to predict that during daytime, we were able to remove pretty much all the acetic acid and all the BFAs. And also that the peaks that we were able to predict were pretty much in the same order of magnitude. And I'd also like to point out that the input wastewater had 2.5, pretty much between 2 and 2.5 grams COD per liter. And here we are talking about 20 milligrams per liter. So very, very small differences. But still, that's something that we need to polish. So take-home messages, and we're going to finish straight away. PPB are oceanic phototrophs, and phototrophy is key for their application. They have very diverse metabolism, which is a challenge for modeling, particularly mixed cultures. And our model was able to accurately predict the responses in their anaerobic and aerobic conditions. And we could also simulate optimal conditions for the finest scenarios that I couldn't show here for we didn't have enough time. And in terms of perspectives, what we want to do is to validate interactions, PPB and microalgae. That has a lot of potential for application. Also, as microalgae will eventually polish the residual nutrients that you get after a PPB system, which is generally limited in COD. And also interactions between PPB and SRBs. And eventually develop a comprehensive light distribution model, and also with a heat transfer model, as Francesca presented, and integrate eventually the model with economic assessment and LCA. And last but not least, I want to thank these guys, mostly Tim Poulsen. This is the main dude working with PPB at the University of Queensland. He has been working on this for years. He's excellent. And also I'd like to thank Damien Basson and Juan Lema, which worked with us in the project. Thank you.
Thank you, Gabriel. Amazing work indeed. This purple bacteria, they are nice challenge for modelers indeed, with all these potential metabolic pathways they can follow. So great job in it. And so this was the last presentation from our expert speakers. So now we can check whether we have residual questions from the audience that were not taken yet or discussed yet in the chat. Let me have a look. So there were a couple of questions for Gabriel from Abraham, and I think they were already answered in the chat. There was a question for Francesca related to alkalinity dosage, and the economic impact of dosing alkalinity. And I think Francesca provided some good numbers just to have a point of an idea of how this may impact the system. There was a comment from Gabriel related to the fact that alkalinity addition is not necessarily always needed. I guess this, of course, depends on the characteristics of the wastewater, of the nutrient source that you are using. I don't know if Francesca, you want to add something around the fact that alkalinity is a specific request need when you're working with diastates.
Yes, for sure it depends on the wastewater characteristic. It's not something that I observe always. For example, for the reactor in Narbonne, where there was the influent was this synthetic medium mimicking a municipal wastewater. In that case, there was not this problem, but at least for the experience I had at the time I was working with digestate, dilute digestate especially, this problem was coming out, and so that's why I'm associating it to influent that are very rich in ammoniacal nitrogen.
Yeah, I guess it's the ratio between alkalinity and ammoniacal nitrogen that matters there. Okay, thank you. Then there was a question from Davide related to which type of digestate was used in the Savannah project, and Gabriel commented that this digestate came from pork manure digestion, and he commented that you can use both the manure itself, the wastewater itself, or the digestate as a nutrient source for algae growth. And this basically the main request is to remove the solids and to improve light penetration. Then there's a comment related to the interaction between light and bacteria and particulate. That was from Olivier to Borja. And I think Borja also commented something related to the light effect that suspensions have depending on the concentration and on the type of microbes that you have there. I don't know if Borja, you're willing to add some details. Further details on that?
I think I just got another question from Olivier as well, in whether we have included this model or not in our, like together with the biokinetic model. And the answer is no, because in the reactors that we run with real wastewater, we did it with pre-treated wastewater. So there was no organic carbon in there. And then we didn't have much competition with bacteria. So we didn't have a big effect of the bacteria in the light attenuation. We actually, the challenge we had was mostly predators that they were grazing on our algae sometimes. But we could use the attenuation coefficient that we had with algae and growing in wastewater effluents. We didn't need to have to combine it with bacteria for this.
Okay, thank you. Quite clear. Yes, there's a missing panelist here because Gabriel Acien, he had to run away because he had some teaching duties. So I'm sorry he cannot be here for the question and answer section. So in case you have further requests for him, we can put you in contact with Gabriel directly. Okay, there's a new question coming. It looks like that all experiments conducted in shallow reactors maximize light penetration, Algae-bacteria constructed reactors. What is important? Is there any interest from the panelists on working on deeper CSTR reactors using supplementary LED lighting? Okay, that's a question related to artificial lighting and phototrophic reactors. I guess their main issue is related to the economic feasibility of adding external energy requests for the growth of biomass, and I guess also related to the purpose of your process, whether you want to produce any very high value added molecule or just reducing pollution of the wastewater. So gas feasibility very much depends on the final purpose of the treatment, but I'll leave the floor to panelists if they want to add something related to this aspect.
We have tested actually in DTU. It's a very cool system where we had like a LED floating inside the reactor. So it was a chemostat that we just had like with mixing and the LED, and that improved a lot the productivity of the algae. But you're right, you need to be able to sell this biomass as a very high value product. So if I think about the context of water treatment, it has to be probably with industrial wastewaters, like from food industry and so on, where you can actually make a good use of that biomass. Then it would be affordable to start thinking about this kind of lighting systems.
Yeah, then the final biomass values depends on how you grown it and whether it was cultivated on wastewaters that prevents a number of potential valorization routes, because of course, regulatory issues related with wastewater products. Any other comment on that?
Well, I remember when we were in Queensland, we checked what would be the maximum biomass efficiency according to light input with the most efficient LED lights that we use. And if I remember properly, we ended up with $1.9 per kilo, if I remember properly, as a cost of lighting illumination, which meant that that was the price that we needed to sell. That was the minimum price that we needed to sell our product for. And at least in wastewater, constant.
Only for lighting.
Only for lighting, and obviously no capital costs whatsoever. And that was far over what we could afford.
Okay. So do you already have some clear final markets for the purple bacteria biomass that can cope with the production costs?
Well, what we have is an idea and a wish of what we would like to sell it for, which is pretty much $1.3 per kilo, and in the case of feed purposes. So that would be the whole idea. But again, with artificial lighting, it's artificial illumination is just not possible at all.
Thank you. We have the mixing aeration tool for deeper algae-bacteria reactors. Okay, so you can check if you're interested in this topic. Asian Kaya is suggesting something for you. And then we have something more coming from Abraham. The photoinhibition, of course, during cultivation. Is there a possibility of microalgae survive repeated exposure? Photoinhibition. Color change from green to yellow. Color restoration was also his experiences some photoinhibition of his culture, and asking whether this inhibition is tolerable, or at which extent it is tolerable by algae. Is anybody interested in commenting the photoinhibition effect? Maybe Borja, do you have any experience of on photoinhibition and recovery from photoinhibition and long-term effect of that?
I think what he points there is also like it's 45 degrees is quite high temperature. So sometimes you have this combined effect of temperature with light inhibition, which makes it even worse. I did not suffer that in my photobioreactor, so I don't know exactly how is this problem. I had an issue, or we had an issue running the reactors in summertime, which, believe it or not, in Denmark sometimes gets very hot, and inside the labs we don't have good ventilation, so the temperature rise from 20 to 26, 27, and we lost the culture, and we had to cool it down, and then we recover it back. So I think in this case, probably the culture is becoming very sensitive to temperature, and that's why it kind of oscillates maybe between something that seems like photoinhibition, but I think it's just becoming more sensitive to light because of the high temperature.
Yeah, I guess the 48 is almost quite a limit for mesophilic microorganisms in general. So you experience some protein denaturation that is almost killing biomass there. So yes, for sure, there's a large effect of high temperature. Then there's some question from Davide. It's been an interest effort using model-based dynamic DOA, design of experiment, to help perform optimized experiments for parameter calibration. And that's a nice question for those of you that have very complex models with so many parameters to be identified and calibrated. So Gabriel or Borja or Francesca, do you want to comment on that?
Go ahead. At least for PPV, not that I'm aware of. I haven't seen any dedicated effort to even dynamically calibrate all the combined processes that I was mentioning. But everything that I have seen is always focusing on one dedicated metabolism. So calibrating specific condition well, basically you reduce the identifiability issues by basically choosing which parameters are going to be affected under, so I'm going to define basically the performance of the model and the conditions that you are using for calibration.
Experience-based design of experiments, so to activate the metabolism, specific metabolism. Then, and Borja, will you have any further comment on that?
No, I think it has been more or less the same approach that we have used for microalgae. We try to design different experiments. We try to design them even in different scales to, for example, avoid light inhibition or being able to control it and so on. But it has been mostly based on our experience that we were gaining all the time on how to manipulate the algae. And the intention here was, as Gabriel says, really to try to identify parameters to the best of the possible extent. When it comes more to like longer term experiments where you just try to reassess the model if it predicts well or not, we usually have resorted back to these protocols from the benchmark on like maybe some sensitivity analysis to find out which parameters are sensitive and then calibrate those.
Right, thank you. Okay, and then we have one further comment from Asian Kaya asking whether anybody has tried MBBR media in photobioreactors, so moving bed biofilm reactors for algae culture. I guess there was some experience from biodiscs, so biomass growing on surfaces. I don't know whether specifically on typical MBBR installations or processes. Have you got any experience of that? Not from this group. Yeah, there are some works that are being done on biofilm, microalgae biofilm. So instead of using suspensions, trying to force algae to grow on surfaces for easier harvesting mostly. And this is something that that are under study, I'm sure.
Sorry, Elena. I wanted to answer to the question of Davide, the previous question.
Yeah, sure. Design of experiment, right?
Yeah, because actually it's what we try to do for the nitrous oxide estimation when we decided how to set up the 3 reactors. In fact, before we ran some simulation to have any idea of which were the exact conditions we would put the 3 reactors to see the inorganic carbon emitting conditions. So in that case, we ran previous, all the condition and the concentration of the addition of ammonium source, of alkalinity source were decided by the model, let me say, by the simulation that we did. And so in this case, we used the model before and after just for validating it, but also for the design of experiment in that case. But it's the only experience I have from it.
Yeah, I think in general, it's very good to have a model to define which is the best way to perform an experiment to observe one specific aspect or parameter process. Yeah. Thank you.
Okay, my friends, I think we are running out of time. We've been going on now for 85 minutes. So I think it is time to conclude. And I just want to, first of all, say thank you to the presenters and Elena, the moderator, for a great show on phototrophic systems. I know I learned a lot. And I hope many of you who attended the webinar did as well. got some new ideas and so on. Also thanks to the audience, and remember that you will have the video of this available if you want to check something again, and you will have the slides from the presenters as well. You will get a link to download those slides as PDF files. A special thanks to a number of members of the MIA Management Committee for arranging the webinar here. And I just want to promote also the possibility for you to listen in on our next webinar, which will be on the state of the art in physical chemical modeling. As you know, I mentioned in the introduction that the scientific and technical report from the task group on physical chemical modeling had just been published, and this will be a webinar related to the finalization of that work and the absolutely latest available information on modeling such systems. And also remember that if you are an attendee of these webinars and you feel that you have something that you want to arrange a webinar on a specific topic that is related to modeling of water and wastewater systems, then you can contact me or anybody else in the management committee of MIA, and we will see what we can do to create such a webinar for you. With that, I want to say thank you and wish you all the best. Happy holidays. We are now approaching the holidays if you are watching this live. So really enjoy a bit of vacation and have a great time, and hope to see you all again in 2023. Thank you. Bye-bye.
Thank you.
Thank you.
Thank you for the
Thank you. Thank you all.
Thank you.
Thank you.